A particle P of mass 2 kg is acted on by two forces F1 and F2. Show that the acceleration of P is 3I plus J. Okay, to find out the acceleration, we need to use the formula resultant force is equal to mass times acceleration. This is the resultant force, not just F. That would be wrong. It's resultant force. And on this particle, there are two forces acting, F1 and F2. So to find out the resultant of the two forces, we just add them up. And why can we just add them up? It's because they are in vectors. In vectors, you can simply add the forces. Okay, so 4 plus 2, that's going to be 6I plus 3 minus 1, that is 2J's. Okay, this is equal to mass times acceleration. Acceleration, okay, we do know the mass. The mass is 2, so 2 times A. Now divide both sides by 2, or more appropriately, multiply both sides by half, because this is actually weird. Like writing it down like this, like 6I plus 2J divided by 2, this doesn't exactly look right to me. So instead, what I like to do is I multiply with half instead of saying just dividing by 2. It's the same thing. So 6I plus 2J's. Okay, and I only do this when we have vectors. Okay, this becomes 3I plus J. There you go. We showed that the acceleration is this. At time t0, P is at the point with position vector 2I minus J relative to a fixed origin O. Okay, so that's like our initial position vector. Okay, so we're doing M2 and they've brought M1 here. Okay, it doesn't matter. Initial 2I minus J. And has velocity. So initial velocity is 4I. Calculated time t is equal to 3 seconds, the velocity of P. Okay. At t equals to 3, so we know we can just do v is equal to u plus at, I think, yeah? And this is 4I, plus the acceleration is 3I plus j multiplied by 3. Okay, now the reason we could use this, v is equal to u plus at, is because the acceleration is constant. It's just 3I plus j. There is no other variable that is going to be affecting the value of acceleration. For example, if the acceleration was 3ti plus j, that would mean that as time passes, the acceleration would be changing. So there's none of that over here, so we can actually use the suvat formulae. Okay, this becomes 9 plus 4, what is that? 39. 39 plus 3j, that's 3j. Okay, so that's the velocity. I don't know why it's 5 marks. That's weird, but that should be the answer, unless I'm mistaken. No, this is okay. Okay, the position vector of P at time t is equal to 3. Okay, this was part B, this was part A. Position vector of P at t equals to 3. So what do we know? R is equal to R naught plus the extra displacement, right? Not just Vt. I know it can be tempting to just say R is equal to R naught plus Vt, but that is only appropriate when you have constant velocity, when you're moving at constant velocity. So we can't use Vt for the extra displacement. Instead, we have to use Ut plus half At squared. So the initial velocity is 4I, so 4I times t plus half times the acceleration 3I plus j times t squared, which is 3 squared. Oh, I forgot to put in r naught. What is r naught? What is the initial position vector? It's 2I minus j. So let's put that in as well. 2I minus j 4ti plus 9 by 2. So that's like 9 by 2 multiplied by 3. That is 27 by 2i plus 9 by 2j. Okay, now we're just going to group all the I components and the j components. So 2 plus 27 by 2. I'm just going to put it in my calculator. 2 plus 27 by 2. That is 31 by 2i plus the 4t we have right here. Okay, wait, why did I write I here? My bad. Okay, and then we just write down I. Same for the j components. Okay, it's just 9 by 2 minus 1, which is 7 by 2j. There you go. That's it. Wait. Oh, I forgot to I forgot to substitute t is equal to 3 over here. Okay, so 12 plus 31 by 2 is 55 by 2. So the answer is 55 by 2i plus 7 by 2j. This is where the particle is at when t is equal to 3. Now, part D says the kinetic energy of P at time t is equal to 3. What is the kinetic energy? You have to ask yourself that first. Kinetic energy is half times mass times velocity squared. And velocity is not exactly the right thing to say here. It's really just the magnitude of the speed, right? For example, let's say this way you're moving at 5 meters per second, but then you change direction and move this way, your velocity would be minus 5 meters per second. But it wouldn't matter, right? Because when you put this into the equation here, the minus is just going to get squared. But this is fine, but what if you have vectors, right? Let's say you have 3 and then 2 here. So that's 3i plus 2j meters per second. Now the problem with this is you can't exactly square this, right? You can't multiply vectors like this. Well, I mean, you can. That's a different thing. It's like cross product. You're going to learn it maybe sometime in the future, but we're not doing that shit over here. But what we can do is take the magnitude of the velocity vector to get the speed. Okay, the magnitude of the velocity vector is speed, and that's what we're going to substitute in this equation to find out the kinetic energy. So velocity is square root 13 squared plus 3 squared. That's it. And then we just put this into the equation. Half times the mass is 2 kgs multiplied by the v squared. Okay, so if you square this, the square root is going to disappear, and then you're going to be left with 13 squared plus 3 squared. Don't forget the brackets. Okay, so they just cancel out. So the answer is just 13 squared plus 3 squared. Wow. 13 squared plus 3 squared. Let's go. 178 joules. Okay, bye.